Math 1332, Chapter 2, Set Theory, Section 3, Using Venn Diagrams to Study Set Operations. Video 5, Using Venn Diagrams to Show Equality of Sets. This is kind of a spin-off of the previous video about De Morgan's laws, but it goes beyond that because I just kind of verbally convinced you that De Morgan's laws might be true, and then showed you some gimmicky ways for remembering them. But at no point did we actually verify that it was actually true. So we're going to do that and then use this technique in general to show whether or not two sets are equal. So to start, we're going to prove the first of De Morgan's laws using Venn diagrams, the first of which said that the complement of the intersection is equal to the union of the complements. So the complement of A intersect B is equal to A complement union B complement. Now, how do we use Venn diagrams to show that two sets are equal? Well, it's really simple. You draw a Venn diagram for the first expression. You draw a Venn diagram for the second expression, and if they're both shaded the same, then the two expressions are equal. I've already got a Venn diagram set up for each, for A intersect, the complement of A intersect B, and for A complement union B complement. And just a reminder, in a two-circle Venn diagram, set A consists of regions 1 and 2, set B consists of regions 2 and 3. So now we're really starting to put everything together. All right, remember to determine the regions to shade for a set expression or a set operation. We need to first determine the order in which to build that expression using the order of set operations. Starting with the complement of A intersect B, we go inside the parentheses, and the only operation there is the intersection. That completes the parentheses, and outside the parentheses, we only have one other operation, that complement. So let's go ahead and figure out this one. First, we need to figure out A intersect B, meaning that if we looked at these two sets and asked what their intersection was, we're simply asking what they have in common. That would be region 2. That's also probably pretty obvious because by now you probably know that the intersection of the two circles is that football in the middle. So no matter how you slice it, the intersection of the two sets is region 2. For the second and final set operation over here, we're taking the complement of A intersect B, meaning that we want the complement of the set that we just found, meaning we want all the numbers in the universe that aren't 2. Well, this universe consists of the numbers 1, 2, 3, and 4. So the numbers that are outside of that, the numbers that are outside of 2, but still in the universe, are 1, 3, and 4. Meaning that we would shade regions 1, 3, and 4. So literally everything except region 1. All right, so there's our Venn diagram for the complement of A intersect B. To see if these two set operations are equal, we have to do the same thing, make a Venn diagram for A complement union B complement. And just like before, we're going to do it in the correct order. There are no parentheses, so we go straight to the complements. We have 2 of them, so we'll do them left to right. A complement first, B complement second, and then the union third. A complement visually is all the numbers outside of circle A, and for some reason, I think I know why, that region number is not red, but it is now. All right, so as I was saying, we're finding A complement, which are all the numbers outside of A, which is regions 3 and 4. Our second move over here is to find B complement, which are all the regions outside of circle B, which is regions 1 and 4. And our third move is to take the union of A complement and B complement. So our third move is to take the union of these two sets. If we join them together, we get regions 1, 3, and 4. And at this point, we already know they're equal because the equality was determined the moment that this set wound up being the same as this one. The Venn diagram just gives us a visual representation. So 1, 3, and 4. So basically everything except that football in the middle. And since the Venn diagrams have the same shaded regions, we have proven that these two sets are equal. So to wrap that up, since the Venn diagrams for the two set operations are shaded the same, then the two set operations are equal. All right, we'll take a look at one more, but it's not just a problem I kind of concocted out of nowhere. It's natural, especially if you have algebra lingering in your mind, to ask yourself, can we do another distributive property? If you take the complement of a difference, is it the same as the difference of the complements? In other words, if you see something like A minus B complement, can you just distribute and say A complement minus B complement? So we're not being asked to show that they're equal. We're being asked, are they equal? But we'll take the same approach, form the Venn diagram, and then see if we end up shading the same parts. And by the way, this will be the last example that we do, but we can also do this for 3 circle Venn diagrams that have 3 sets. It would just be more work because we have larger sets to deal with. All right, so let's start with A minus B complement right here. We have parentheses, so we'll go inside and do the difference first. And then outside we have the complement, so we'll do that second. Oh, I invite you, as usual, even when I don't say it, I invite you to pause the video, see if you can complete both Venn diagrams and determine if these two set operations are equal. All right, so for first, we'll do A minus B. So we'll start with set A, which has 1 and 2. Cross out anything that belongs to set B, that would be just the 2. So A minus B is region 1, excuse me. But then again, you may remember that if you remember earlier when we talked about this right moon, this region being the region for A minus B. Our second move is to take the complement of that. Well, the complement of region 1 would be everything in the universe that is not region 1. So that would be 2, 3, and 4. Don't forget region 4 is out there. And now we know what to shade over here. Let's shade regions 2, 3, and 4. So everything except region 1. And again, the shading doesn't have to be perfect. I should have used my stylus instead of my mouse. When will I learn that lesson? Eventually. All right, so there's the difference of A minus B. The complement of A minus B. All right, now for the other one, we have 3 operations. We have 2 complements and a set difference. There are no parentheses over here, so we'll go right to the complements. We'll do A complement first, B complement second, and in the middle, we'll do the set difference third. The complements are pretty easy. A complement is still just set 1. B complement, I'm sorry, what am I saying? A complement are the numbers outside of circle A, so it doesn't include 1. Sorry, I was looking right here for some reason. A complement is going to be everything outside of circle A, which is regions 3 and 4. The second, B complement, is going to be everything outside of circle B, which is regions 1 and 4. And finally, we do our set difference, A complement minus B complement, which means we start with A complement, which was 3 and 4. And we cross out anything that's also in B complement, that would be 4, because B complement has 4. So A complement minus B complement is just region 3. So what's the answer to the question? Are the sets equal? Well, the answer is a resounding no. Hardly. So to summarize, to verify that 2 sets are equal or explore whether or not they're equal, you simply draw a Venn diagram for each one using the techniques that we've already developed. If the Venn diagrams match in terms of shading, then the sets are equal. Otherwise, they are not.